All right. So this first lesson is not actually too difficult. We're just talking about limits. Was it you that was asking me, or maybe it was you that was asking me about how can we know if there's a limit? And I was saying that we can't really know for certain because the maths involved is quite complicated. But there is one exception. We can actually know if there's a limit if the sequence is geometric, and that's what we'll start with, okay? So have a look at these two geometric sequences. Are you worried about that fly?
Is that a fly?
It is a fly.
That's the one.
That's dude. Dude, that's a blue bottle. Hang on. Let's see. Person who's been indigenous to Ireland for several decades versus people who have been here for a few weeks. I am telling you that it's called a blue bottle fly. It is not a wasp.
So I
Stop! Leave the poor fly alone. It is not dangerous. Would you leave the fly alone? It is not dangerous. Your reaction is ridiculous. It's as if you're reacting to like imagine it's a butterfly. Picture it's a butterfly, except it likes to eat dog poop. That's the only difference. Okay? Right. It is gross. Okay. So limits. So as I was saying, let's have a look at geometric sequences. So consider this geometric sequence. We'll say 4, 2, 1, a half, a quarter, an eighth, etc. And then consider this geometric sequence. 1, 2, 4, 8, 16, 32, etc. Now they're both geometric. In the first case, what's the A? Yeah, what is the A? 4. And the OR? A half. And in this one here, what's the A? 1. And the OR? 2. But this sequence is convergent, and this one here, divergent. And actually the reason is because of the OR. Now if you think about it, that makes sense. Because if you keep multiplying by 2, all you're doing is making something bigger. But if you keep multiplying something by a half, you're making it smaller. So, we have this very simple result.
The first one is a limit of 0.
It has a limit of 0, correct, yes. Yeah. You see, it's great stuff. So, we have a limit if the OR is between -1 and 1, like in the first example. And the second one, we have no limit if everything else. So, how can I write this? If OR is not between -1 and 1. Okay. Yeah, this is not the set -1 to 1. And that's it. So if the OR is 2, divergent. If the OR is 0.6, convergent. So this provides us with a simple way of knowing if a sequence is convergent or divergent, provided it's geometric. So let me just do one example. You can tell me. Consider this series 1 plus 6 over 7 plus 36 over 49. Is this convergent or divergent? Well, again, we might just say we should look at the OR. And what's the OR here? 6 over 7. So what does that make us think? It's convergent. However, well, no, it is convergent. However, in my example here, this was only for a sequence. Perhaps this doesn't hold true for a series. Perhaps with a series, because you keep adding, it might be divergent. So we need to talk a little bit about, does this work for a series as well? So let's take a look at the formula. If I want to calculate S infinity, which means I add up all the terms forever, then if I look at this formula, there's a way I can do it. But what's the n in this formula? It's infinity. Now you realize we... Oh, sorry, I should have put the n on the top. Thank you. N on the top. So that's a 1 minus or infinity over 1 minus or. Now you realize it really comes down to this, okay? Because think about this. If the or was 2, what is 2 power infinity? Infinity. And so the s would be infinite. But if the or was 0.5 power infinity, what's that? Does anyone know? It's towards 0. Now you can... No, the 0.5 infinity, you can check this on your calculator, okay? Like if you have, look, 0.5 power 1, right? Power 10. Power 100. What's happening? Yeah. In fact, the calculator has rounded down to 0 at power 1000. So once again, it's the same result. It's the same result. If the or is between -1 and 1, both the sequence and the series converges. If the or is outside of this range, then both the sequence and the series diverges.
So it's 0.
So actually, yeah, that or infinity is 0. So we arrive at this formula. If you want to add up everything, it's simply a over 1 minus or. So this is what you might call, the limit of the infinite sum. It's as if you could add all the numbers forever. You don't get infinity, you actually get a finite number. So for this example here, let's calculate it. If I was to add every number up here forever, don't stop, continue forever, what would I get? I would get a over 1 minus or. So that's 7. So it seems quite amazing. If you add all these numbers up forever, the total will be 7. Not infinity, it'll be 7. Let me give you a small one to try, just to make sure. Yeah? Oh, because or infinity is 0. Yeah. Try this one, okay? I want you to do 1 plus a half plus a quarter plus an 8. Continue forever. What does this equal? Well, firstly, is it convergent or divergent? It's convergent because the or is a half, so we can legitimately ask what is the total here. So calculate the total, please. Yeah.
2.
Is 2. Yeah? Because it'll be a over 1 minus or, which is 2. Now, you may or may not be thinking, how could a infinite sum not be infinite? Like, how come this is only 2 and exactly 2? I can give you a little picture to help you. Can I scroll down a little bit? Right, so, let's see. Grass. We've got a brick wall in here. The wall. Distance from here to here, 2 meters. And let's see. We'll make this a frog. That's a frog. Okay. Right. So I want you to imagine the frog moves 1 meter. Okay. Then, basically the frog can only hop half the distance to the wall. So it's 2 meters from the wall, so it can only hop 1 meter. So that's its first hop. Now, how far away from it is it now from the wall? 1 meter. It can only hop half the distance. So it hops now 0.5 meters. How far away is it from the wall? 0.5 meters. So how far will it hop on its third hop? 0.25. Now, if you could imagine this process forever, it never quite reached the wall. But if it could do this forever, how far would it have travelled? 2 meters. 2 meters. Yeah. That's what's happening here. There's a 1 meter, then half a meter, then a quarter of a meter. If it travelled an infinite distance, then it must then have passed through the wall at some point. But we know it can't do that because it's only able of hopping half the remaining distance. So this can never be, it cannot be infinity. It cannot be infinity. It can be 2. It can be less than 2. Certainly can't be more than 2. Yeah? Okay, you want my frog picture, is it? 11, nearly 12. Yeah? I like to visualize it this way. If you're a visual person, perhaps you'll appreciate it this way. Okay, so next example now. Can I scroll down? Yeah? Yes? Okay. So, let's take this sequence here. What I want you to do for me is to give me the first, using your calculator, give me the first few terms. And I tell you to start at 3. And let's see, give me up to 4. Okay, what's the next term after 3? 8. Yeah? Next one? 7. Next one? Like 5.84 or something? 5.86? Is this right? You don't seem... Here, let me... They told me. I'm listening to my students. I shouldn't listen to students. You're right. No, you're right. No, screw the students. Yeah, I'm not listening to those guys. Right. 3. Okay, so what's my formula here? 5 plus 6 over 3. So the next one is 7. Okay. And then the next one is, as a decimal, that's 5.857, we'll say. 86 then, okay. And then the next one is 6.02. So if you were to look at this sequence, what would you say? Convergent or divergent? Well, which? If you're not certain, let's do one more. So, U5. 5.996 basically. Yeah. It really looks like it's convergent to 6. Okay, so we think the limit is 6. But how can we calculate this for certain? Like, it's possible that the limit's not 6, right? Like, the limit could be 6.001. We can't quite tell with this. So, well, no, not necessarily, because the calculator has a rounding error. You know, it's possible that it's not exactly 6, and we miss this because the calculator rounds off. You know, for example, is 0.5 power 1,000? Is that 0? No, it's still a number, although a small number. The calculator has said it's 0. Okay, so we need some way of knowing if it is exactly 6, and we need to calculate it. So how can we do that? Well, here's the trick. Can I scroll to the side? Yeah. Well, actually, no, we'll go back to the numbers here. What's happening to the difference between each of these? Well, what would you describe as happening to the difference between them? It's reducing, isn't it? So would it be fair to say that neighbours get closer together as you approach the limit? Yeah, because if we even go back to my frog picture, as the frog gets closer to the wall, the neighbouring hops, they're not much different. In other words, you have this, I don't know if you know this expression, diminishing return. Do you know diminishing return? It means each extra step gives you less and less. Okay, so as we approach the limit, we have we diminish, meaning that we start making smaller gains. So, okay, we don't quite get to the limit. I know this, but imagine that we could get to the limit. Then there should be no difference between the neighbours because we are at the limit. Yeah. Like imagine the frog did make it to the wall, then it would no longer hop because it can only travel half the distance to the wall, and the distance to the wall is 0, so no more hopping. Okay? So let's imagine we could reach the limit here. Yeah? That's 25 past if you need to go to the bank. Imagine we could reach the limit here. What would you describe as the relationship between un and un minus 1? How would you describe those neighbours? Close. In fact, perhaps equal. In other words, my point is u infinity and u infinity minus 1 are the same thing. Yeah? If you were at the infinite term, then that should be no different than being at the infinite plus 1 or minus 1 term. Now the language is quite complicated because you can't quite be at the infinite term. You can't quantify it. But to try and conceptualize it. Yeah? Are you going to the bank or what? Yeah. Yeah? What's wrong? Yes. Yeah, I know. It's I'm deliberately using bad English to try and help you understand. We don't reach the limit. We imagine we reach the limit.
You just looked up what I said.
Yeah, no, I realise you're not going to like me. Okay, how about this? N is large. Therefore, un is roughly equal to un minus 1. Would you agree with that? Yeah. In fact, if you look at this situation, 4 and 5 are small numbers. True? But even at 4 and 5, would you describe the difference between the neighbours as big or small? It's small. So imagine if I had u1000 and u999. Would they be close or far apart? Very close. Very close. Now, if I'm not saying we're at infinity, but if we could keep thinking of this logic further and further and further, u a billion, would that be much different to u a billion minus 1? No. And what about u infinity and u infinity minus 1? Like, what is happening? They're approaching a point, they're approaching a situation where they're equal. So we can call both of these x, because they're the same thing. So if I go back to my original equation, I can think of this as being like x equals 5 plus 6 over x. I am looking for an x that makes the neighbours the same, or practically the same. Yeah? This is a formula that relates the neighbours. I'm looking for a solution to this formula that makes the neighbours practically the same. Yeah? Some of you will get this, some of you will not. Some of you will need to drink herbal tea and reflect on this. Okay? You don't like this. No, I know. You definitely don't like this. Yeah? You like this. Yeah, okay. So you need to reflect on this, okay?
So would it be more than 6?
Let's calculate. So, I want to solve this guy here for x. What should I do? Multiply by x. X squared equals 5x plus 6. X squared minus 5x minus 6 equals 0. This has two solutions. Let's factorize it. We have minus 6 and plus 1. So x equals minus 1 or 6. That's what we thought. So the limit is either minus 1 or 6. Which do we think is the correct answer and which is the wrong answer? 6. 6. It's 6. The limit is 6. It approaches 6. Before I answer that, yes?
Why 46.02?
Where? Which one am I looking at? U4, 6.02. Yeah. Yeah, it jumped over the 6, didn't it? Yeah. So in this one here, it's approaching the 6 like this. If this line represents 6, then what the sequence is doing, it started at 3, didn't it? It went up to 7, down to 5.86, down up to 6.02. It's kind of going like this. Yeah. It never quite hits the 6. Huh? It never quite reaches the 6.
The line can't cut the asymptote.
No, it can. In this one, because it's oscillating, it can. You're thinking of situations like this. You're right. It can't cut the asymptote there. But in these oscillating ones, the asymptote can be in the middle. It can be like a vibration around it. So this is an asymptote you haven't seen yet. Yeah. But you can't have that. Okay. So anyway, the point is, to find the limit, you simply substitute in an x for this and solve. And that's it. That's the idea. Yeah?
The answer is 6, right?
Yeah.
You said we approach it,
Yeah.
but we don't reach it.
Yeah, this is exactly like the conversation I had in the last class with him. Do you want to explain? Or, yeah, so...
No, sir, you reached it.
No, I didn't reach it.
Yeah, but she never hit 6.
I never hit 6 exact.
So it can pass 6, but doesn't mean it.
It can pass 6, yeah.
So isn't that approaching, approach, pass?
Let me
Approach can mean from either directions. You know, so like, imagine I was to say I approach the post office. Usually we imagine I get closer and closer to the post office. But I could do something like go past the post office and walk back to it and then miss it again, but then get a little bit closer, you know. I can still approach it in this sort of way.
So
We never land on 6.
okay.
We never land on 6.
We can go past it, but we don't land on it.
Yeah, we could go past it and skip it and not land on it. Yeah. It passes 6, yeah. Yeah. Yeah, no, it can pass the limit. The problem is with the vocabulary, because in English limit...
I got it.
You got it? Is that okay? You've reached a higher level.
Explain to her after class.
Okay, alright. Thank you. Alright. Can we go on to the next example then? Yeah. I mean, this stuff isn't easy, you know, like, I mean, this maths was only developed around about, 1820s. It's quite recent compared to other maths. And the reason for its late development is it's very difficult concepts to understand. You know, the people of the 1800s likewise had difficulties accepting the concepts that we're talking about here. They're not obvious. They're not clear, you know. It's not like 1 plus 1 is 2. I have a thing, I have 2 things. Okay, it's much more complicated than that to imagine. Okay, but that doesn't mean we can ignore it. Okay, next one now. So let me give you this sequence. This one is a little bit of an easier formula. 6n squared minus 7n plus 8 over 3n squared minus 5n. Yeah. It's the last one in 3. I want you to give me the first 4 terms again, please. Now, you have to type in the n as 1, 2, 3, 4.
First one's 37 over
37 over 4. What's as a decimal, please?
9.25.
Okay, next one. What's the next one there?
Sorry, excuse me.
Yeah.
When you want, you just put 1 inside the n,
Yeah.
and that doesn't give you.
I'm assuming my students are telling me the truth. Is the next one 9?
No.
Are you sure? Okay. Next one. And one more. Oh, look at.
The second one is 18 over minus 4.
As a decimal?
Yeah, which is minus 4 over 5.
Ah, no, it couldn't be minus. It can't jump that much. Well, maybe it can. What is it? Guys, I don't. I'll do it myself. No, I'll just do it myself. Can't trust anybody nowadays. Right.
Yeah.
So, no. Okay. Well, we'll both be right then. Right, so I'll do it as, I'll just type the formula in. 6 alpha x squared minus 7 alpha x plus 8 over 3 alpha x squared minus 5 alpha x. Okay, I'll start at 1, I'll finish at 5, and I'll go up in 1s. So my first one is minus 3.5. Minus 3.5. 9. Yes, congrats to you. 3.42. And 2.71. And then 2.46. Now, what do we think this is doing? Is it convergent or is it divergent? And if you were to estimate the limit it is trying to reach, what is it trying to approach? Well, this is interesting. Maybe it's 2, maybe it's 2.5, or maybe it's 3. So we need to calculate it. But we think it's somewhere between 2 and 3, somewhere around here. But I mean, it's possible. I mean, it could actually be maybe 0. Maybe it's getting smaller. Okay, so we need to calculate it. So, what happens if the n gets bigger and bigger? Well, let's imagine we put in a really big number for n. So, really big number here. Goodness, I sound like Donald Trump. Okay. So, we put in a big number here. If you have a big number squared, big number squared, big or small? Big, and this is big. Now, this is a square and this is not a square, so will it be big or small? It should be big. And down below? Big. Yeah. And this is not enlightful. It's not enlightening. But there's a little trick you can do here that really helps you see what the limit is. And the trick is, you simplify this fraction. And you simplify it by dividing by n squared. Everything divided by n squared. So, No, no, like each term divided by n squared. So 6n squared divided by n squared? 6. And the next one? Yeah, and the last one is 8 over n squared. And then here? 3 minus 5 over n. Now, it becomes more meaningful if we consider what happens as n increases. So if I was to make it a very large number, 6 obviously doesn't change. It's always 6. But what happens to this guy? It gets smaller. And this one? Smaller. And here? Yeah. So it's approaching 2 by examining what happens to each term. Yeah. Yeah. 2. Yeah. Yeah.
What did we do divide by n squared?
It's,
We just use the first formula.
you can't see what it's approaching. You know, it's not as clear as if you were to write it in this form. You know? Yeah.
In examination, you want us to do 5 terms?
For this particular one, it's not necessary because there is no choice to make over what the limit could be. It can only be 2. So,
But in the other one.
yeah, you would need to get some terms. 1 sec, yeah.
When you say u infinity, don't you have to replace the n with infinity?
Yeah, which I've done. 7 divided by infinity is 0. 8 divided by infinity squared is 0. And 5 divided by infinity is 0. Yeah, so basically I'm using this rule. A number divided by infinity is 0.
What if it were infinity divided by?
Yeah, that's the problem we had a moment ago, which it's undefined. It's undefined. So we need to manipulate it to prevent that from arising. And the way to do that, in this case, is to divide by n squared. In other words, divide by the largest n power. Yeah, question then? No? Okay. Right, one more example to do now, please. You can write this down, yeah? Can I scroll down? Yeah? Yeah. Right, so the last thing I want to do, do we have that now?
Yeah.
Yeah?
Just write it out.
Yeah. Yeah. Note to self, mind blown. Yes?
No. Just
Okay.
writing rules down.
Okay. Now, last thing. Consider a number like this, and it keeps repeating. This is actually a rational number. What I mean by that is, it is possible to write such a repeating number in the form of a whole number divided by a whole number. Now the question is, what are those whole numbers? In some cases it's plainly obvious. Like if I have this, what is that as a fraction? That's 1 over 3. Okay? Or if I had something like this, what's that? That's 1 over 2.
So is
Is that a rational number?
Yeah.
this is like recurrent decimal.
Yeah, recurring decimals, yeah. If you have a recurring decimal, you can write it as a fraction, as a rational number. For example, if I had something like 2.6666 what's that? 7 over 3, isn't it? No, 8 over 3.
Or 0.1111.
Yeah, 0.1111, all the repeating, that's 1 over 9. So anyways, back to my original question, can we figure out what the fraction is for this? And there is a technique which I'm going to show you. Okay, so let's have a look. 0.121212, etc. What you do is you write that first as fractions. Or, okay, before that, I'll separate it out. This is the same thing as 0.12 plus 0.0012. 12 plus 0.000012 plus, and it continues like this. Okay? Now, let's write 0.12 as a fraction. What would that be? That's 12 over 100. This one is 12 over 10,000. Oh, sorry, that's a plus. This one here is 12 over... Is it? A million. Yeah. And so on. Now, if you look at this, this is what we did in example 1, isn't it? It's geometric. It's geometric, and what's the A? And what's the R? So, by using the formula I gave you earlier, A over 1 minus R. And this simplifies to 12 over 99. I can put 3 in there. 3 goes into 12 4 times, doesn't it? And that's 33. So my 4 over 33 should be 0.1212. May I check, please? Let's see. It is? Yeah. Yeah. So you can see here, 4 divided by 33. Yeah. I've only seen this one in the exam once, maybe twice. It's not so common.
Sorry.
Yeah.
Yeah. Why are we jumping 2 zeros? Why don't we just do like 1 0 1 0 1 0?
1 0 1 0.
0.12 and 0.0.
Slow down. Are we talking about this line?
Yeah.
Okay, so your suggestion I write it as what?
I'm saying like, why did we jump 2 zeros?
Here.
Yeah.
Here. Because of arithmetic. 0.12 plus 0.0012 is 0.1212.
You can do it easily.
Some people might need to do this. Okay. So, there you go. 4 over 33 is 0.121212, etc. Okay, there is another way to do this, but in the exam they actually want this method because it's in the exam question on sequence and series. But there is another method for doing this. I wonder if anybody knows it. You've seen it? What's the trick to it?
I don't remember it, but I remember you make it 12.12.
Yeah, you have to multiply by a 10 in it. Yeah. Just for completeness, I'll show you the other method. It's actually a little bit easier. If the exam question doesn't specify the method, you can do this. But I suspect that if they had this question, they would say something like, by using geometric progression, find the rational number. But I want to show you the other method just in case. Can I scroll down? Yeah. Okay, so here, I think I can remember it. You have the number 0.121212, etc. And I'll just call that x. Okay. Now I will multiply by 100, I think, to make it 12.121212, etc. It's like this one, yeah. I'll do a minus now. 100x minus x, what's that? 99x. 12 minus 0? 12. And all these decimals obviously cancel because they're the same. So then x equals 12 over 99, which is 4 over 33.
Why don't we just put 1?
Hmm?
We put 1 instead of 100.
If I put 1x, what's x minus x?
No, then divide.
What's x divided by x?
1.
Yeah. In other words, I'm trying to keep an x here. I'm trying to keep an x and delete the decimals. That's my goal. Keep the x and delete the decimals so I can find the x.
Now, if you divide 0.121
Yeah.
by 1, so it's 1 over.
I'm not following you. Oh, you mean get the reciprocal
Yeah.
of 0.1212? Oh, I see. On the calculator. Is it? Like, you do this. Yeah. And that should give you 33 over 4. Does your calculator tell you this?
Yeah.
I don't think that's a valid method, because that basically amounts to saying, I asked the calculator what the answer was and it told me.
Yeah.
Yeah.
Isn't that like?
In fact, it might be possible that if I just type in this,
Some calculations actually have the reverse divided.
do they?
Yeah, some have the where.
Hang on, I'm trying to get all my 1-2s. Hold on. Right.
No. Yeah.
Okay, so I have an even easier method. You type it into the calculator and press equals. So no to this method, okay? No to this method. Right. Anything else with this? No, it's a good way to check the answer. Yeah, you can check the answer.
But like, you don't get a mark for working with it.
I don't think you'll get any marks for just doing this. Yeah.
How can I get mine? How can I get the mark?
Well, you could do it like this, with the axis, or you could do it with the previous method.
So you should show steps in the process.
I mean, if the question didn't specify the method, what I wrote down here would be fine. Well, obviously not this part. Yeah? Yes?
Could I please ask a question?
Yeah. 42. Okay. I'll let you try these for a few minutes. I think part A, 1A, 2A, 3A, and 4A. Now in 4A, I want you to use the geometric method, even though the answer is obvious. Pretend you didn't know the answer in 4A.
All the questions?
No, 1A, 2A, 3A, 4A. Yeah. Okay.